Hello, everyone. So I will be talking about quantum logic first, and then a bit about ghosts, which is one extension of my own. Since we have a very mixed audience, I will start we'll spend probably most of the time not on my own results, but on kind of general basic things about quantum logics. Because I guess I think there are probably many who don't know what logics are, there are many who don't know how quantum works. And then I will probably be a bit more advanced on my own stuff, but we will see how it goes. So, the overview I have already just said. So, let's start chapter 1, logic. What is Hoare logic? So Hoare logics are a concept that is used when we analyze a program on a computer. So, or program, maybe some hypothetical, theoretical programming language. So a Hoare logic relates a precondition and the post-condition of a program. This is best illustrated by just giving an example. No mouse pointer, no laser pointer. So here it says the precondition is x equal 1. And then if I run the program that sets x to x plus 1, so increases x, then after I run this program, x is 2. This is like not a very surprising fact, but just to illustrate how one expresses things about programs in Hoare logic. So more precisely speaking, it would be say if the memory of the computer satisfies that x equals 1 before running the program, then it satisfies x equal 2 after running the program. And of course, the program in the middle could be something very complex, and the condition on the sides could be also something very complex. So why do we need such a Hoare logic? There are several purposes. One, we might use it to just describe what does the program do? Even if I don't want to reason about it, I just want to tell you I wrote a program, and instead of writing something vaguely worded that explains how this, what this program is supposed to achieve, I want to be able to give you a very precise, mathematically meaningful statement about what the program achieves. Then the second thing we can achieve with Hoare logic is to reason about programs. So once we know what we claim that the program does, we can give a proof without ever having to leave the Hoare logic. And so there are chat things happening. If there's something in the chat that's important for me, maybe someone will tell me, because I will not be looking at the chat. It's to reason about programs, and without having to go to some other meta logic or whatever, you can do it inside the Hoare logic. And maybe one can even see something more abstract about it. It's not about computer programs, but generally about like reasoning about processes that have some effect on some global state. So for the ones here in the audience that are not interested in computers, you could think about it as we have some process and we ask how it modifies the world and what holds before and after. So let me give I will give some examples of the different things. So first, if you want to give a specification of what the program does. Here I wrote a very simple example specification. Let's say we have written a program called quicksort. And what it's supposed to do intuitively, it takes some input x, which is a list of values, and it's supposed to return the sort distance. And we could say it by saying, like, assume the set of x, by this I mean the values inside x, but not looking at the order, so taking the list but seeing it as a set. If it equals some x0 and we run quicksort, then afterwards set of x is still x0, even though x may have changed, so it contains the same elements, and x is a sorted list. Because if I'm really precise, I would probably need to define sorted and so on, but this is just to give you the intuition. So this would be an example how we can specify what the program does, and it can be done in a clear mathematical logic. But of course, we need to ask ourselves then questions like, well, how do I define these things? What are pre and post conditions? Well, in the classical case that we are still looking at, we're not looking at quantum, this is a relatively easy question because all that we need here is just predicates on memories. So given a memory that is assigning values to variables like x is 5 or y is 10 and so on, it's just a formula that we can evaluate on the memory hypothetically and say whether it's true or false. So that's a relatively easy concept that we are dealing here with, but it will become a bit more involved later. So just to remember, we need to understand what are pre and post conditions, in our case, just predicates on the state or memory of the program, and then we have a program in the middle. And once we have that, we can give some meaning to such triples. Now, I said we can use Hoare logics for doing actual reasoning. And I'm going to give you a simple example how we reason about a program using Hoare logic. So the program I'm looking at is here on the right side. It has 3 operations. And what I claim is that if x is equal to x0 and y is equal to y0, and I run this program, then afterwards x is equal to y0 and y is equal to x0. So I'm claiming this sequence of operation swaps x and y. And how do I prove this? Well, if I start with a precondition x is 0, y is 0, then I run this little one-liner. Then I have, so this is one Hoare triple, the first 3 lines, which says if this holds and I add y to x, then x is x0 plus y0 and y is y0. Again, intuitively very believable, but of course we have some explicit reasoning rules that allow us to derive this step for elementary things. Then we have another step that if now I subtract x from y, then y is y0 minus x0 plus y0, so it becomes x0, and so that's the second Hoare triple. And then a third one we get here, and then we have, well, if we have this chain of Hoare triples, we can plug them together and know that from this very first line we get to the last line by executing these fragments. Of course, this is a very simple program. In general, it could be a complex one. It could involve if statements, or branching, conditional branching. It could have loops. In more advanced languages, maybe it would even have a probabilism in it and so on. But I don't want to go into that. Of course, now here I just was claiming that if the first line holds, then the second line will hold afterwards. To show things like that, we need a bunch of rules. And there are many different flavors of Hoare logics. Depending on the flavor, things may look, the exact rules may look different, but in principle it's always something like this. So in the example that I showed you right now, we basically used 2 rules. One is the sequence rule that says if we have A and run C, then we have B, and we also have that if we have B and run D, then we have C, then it follows that if we have A and run C and D in a row, then we have C. So again, very good rule, probably also not very hard to prove. And here a little bit more complicated rule, like when we had like this assignment, like X is assigned some formula. How do we derive that? Well, we know we have that this thing down here, this X, this A becomes B, holds if and only A is a predicate that implies B, where we will substitute E for all occurrences of X. So that turns out to be the rule that we use there. I mean, it takes a little of mental acrobatic to see that it actually justifies all of the things I wrote there. We can do it. How do we get these rules? 2 ways. Either it could be axiomatic. So we could just say, these are the rules for our language. Believe me, at first it sounds like we're just doing some unproven stuff, but there is justification to it because it basically just means that we are defining the semantics of our language in terms of Hoare triples. I think the original paper by Hoare was actually a axiomatic. I've never read it, but the title says something more axiomatic, so I guess it was. So you can actually define what your language does by giving suitable rules, or you can specify what your language does in a different way, for example, in terms of giving a mathematical description, what kind of function it is when applied to a memory, like what memory is mapped to what memory by running this program. And then for every rule you have, you just prove that this is a true statement. Like for example, once you have a definition of these triples up here, mathematical definitions, you can prove that the thing above the line implies the thing below the line, oops, always. So these are two approaches. I prefer the lower one where we prove the rule sound, but you may encounter the other way sometimes too, maybe. So this was a speed high-level view of what Hoare logic is. Is there any quick question maybe at this point about it that might be needed to continue? I mean, no big question, I think at least should be at the end. Quick clarification needed? No, okay. I was clear or incomprehensible. So now we come to the second part, quantum Hoare logic. Now this is a bit more challenging because we need now not only to understand what Hoare logic is, we also need to learn quantum mechanics. So let's wrap a few semesters of physics into a few slides. So first slide is explaining all of quantum mechanics. So in the classical world, where no quantum mechanics is involved, you can typically describe the state of a system. Here I'm thinking of some computer system with variables, but, because I'm going a bit by example, just by saying explicitly what's in it. Like, for example, we have three variables, x, y, z. Then I can describe the state of the system by saying, like, x is 1, 2, 3, y is 3, 8, 3, and z is 6, 3, 3. Yeah, and that's a description of what the memory contains at any point in time. And then if we say something like I increment x, then I will know it's afterwards 1, 2, 4, 3, 8, 3, 6, 3, 3. And that's how, on a very high level, computers work. And how the world works, in a sense, the classical world. But now, why did I say that? I mean, it sounds kind of like almost a tautology, but I'm saying here, like you describe the state of the system by saying the thing that's in it. Well, it becomes interesting when we compare it with the quantum world. So in the quantum world, the state of our system, we can have states that are just by listing, like for example, variable x contains this, variable y contains this, and so on. The only difference is that I put them not in a round bracket, but in these funny brackets, which is called a cat. But that's just, so far, just notation. I mean, there's deeper meaning behind it, but at this point, it's just notation. So this is what I would call a classical state of a quantum system. It is in a state that looks like a classical state. But in quantum mechanics, we can also have superpositions. So for example, we could have it could be that our memory is both in this 1, 2, 3, 3, 8, 3, 6, 3, 3 state. So these are the values of the variable. But at the same time, it's also in well, some other numbers state. So it's in two states at the same time. And we have some weights, how much the state. In this case, we have 1 over square root of 2 much is how much the first one, and 1 over square root of 2 is how much the second one. These happen to be complex numbers, and it happens to be that the sum of the squares of the absolute values of these numbers have to add up to 1, but you don't need to know that to understand. Basically, just take the idea that a quantum system is not like one definite state of this kind, but can be in many of them with suitable weights attached to it. And from a kind of logical, mathematical point of view, the crucial difference probably between the two settings is that in the classical world, the natural structure of the state of the system is basically a set. There's a set of different values that we can have. And a set basically, like in category theory, set means kind of doesn't do anything interesting, it's just values. While in the quantum world, the structure is different because we can have these sums of different things. The actual structure is a Hilbert space, or a vector space, if we simplify a little. So it's something where we can add states together, and they are like new states that are like at the same time and so on. So you have a different mathematical structure, and because of that, in the Hoare logic, we will have also a different form of predicates.
So what does plus mean exactly?
Plus? Well, formally, it just means that these things are kind of vectors in a vector space, and you the problem is there are like probably a dozen equivalent explanations what it could be. Maybe the simplest is that you just think of it that you could write a state by giving a number for every possible classical state, and then this just says that it gives this much to this one, this much to this one, and 0 to everything else. So, and this means that you can also add them by just adding numbers of the corresponding components.
So,
Yeah.
so maybe just to clarify, it's not that there are two states, and the first one doesn't have the plus attached, the second one has, but the plus is really the binary, right?
Yeah, exactly.
Your overall mixed state of the.
Yeah. Of course, I could also have a minus, but that would be just plus, then minus 1 over 0.
Without proposing these two weighted things.
Yeah. Okay, so what does this? So I was just, so the slide before was quantum mechanics. Now we come to quantum programs. Again, at an extremely high level view, because defining this all precisely is, it's quite, I mean, there's a lot of concepts that need to be introduced. But on a high level view, a quantum memory, quantum program is basically just a computer program which operates on a memory that is not a classical memory where every variable has a definite content, but instead it operates on a memory that is quantum. So it can be in a superposition between many different classical memory contents. And what operations can you do on these things? Well, basically anything that physics tells us is okay to do. I could give you exact mathematical definitions of exactly what operations are allowed to do and what not, but we don't have the time for that. Basically, just take that not every operation, not every function from memory to memory is allowed. Certain are allowed, certain are not allowed. And that's what makes quantum computing interesting, because you need to figure out, can I do something great using the operations we have and other interesting constraints. But what you get in some cases is a large speed up over what you can do with a classical computer by this kind of parallelism, because now your memory doesn't contain just one input. It can contain a huge number of inputs at the same time, and we can kind of operate on all of them, which sounds really great, except that we can't read out all the results. So in many cases, you will just have something massively parallel and then not get the results. So then you need to do very tricky things. Yes?
Maybe a lot of this is what I always find confusing about these explanations of quantum theory, that it's clean. We have all these states at once, and then you think, oh, I have factors and much. It's not like this because we don't really have that. They are, so to say, they are with a certain probability, and at the end you get only one of them. I think the trick is that by going to this next state as an intermediate state, you can play certain tricks. Always
yeah. I mean, saying that there with a certain probability can also be misleading.
Because of complex numbers?
No, not just because of that, because the different branches can interact. While your probability distribution, they really will never be joined again. So it's very subtle, because it's just something that does not exist in the classical world. And therefore we can't really conceptualize it. We can just do the math and it somehow works out. But basically it is something that they are somehow there, but they're not accessible, I would say. Yeah, that's.
So I mean, in the end, you get something definite only one, but since you can use these strange states as intermediate ones, you can go different rules that you just can't go past.
Yeah, I would say they're all there the whole time because I have a probabilistic check. I mean, not the one that works always, but I can kind of test whether like if I have in mind what it should be, what's there, I can test like the whole state. But maybe we should, I'm happy to talk about this later. But, you know, yeah, so basically the message is it's all much more complicated than one thinks. Okay, but quantum programs are also interacting from a purely logical point of view, not just in terms of like speeding up things, because I mean, quantum mechanics is describes how reality works as far as we understand it in today's physics, and quantum programs are basically a small but very precise representation of things we could do on the physical world when we don't want to get bogged down in messy details like what is an atom and so on. It's basically like, what can I do purely on information? And in that sense, it is a purely logical question about logical things that has nothing to do with computer implementations and so on. Okay, so if we want to describe quantum programs more precisely, what is a quantum? What does a quantum program do? Because I don't want to introduce an actual language, but on a higher level. So it takes some quantum state, so something that is like a memory state described in this way that I described. It does something, it returns a new state. So we can say a quantum program is just a function from a Hilbert space to the same Hilbert space. Yeah.
That's the meaning of the program. And the program is something syntactic, and that's the semantics you talked about.
Yeah, I mean, it depends. It's again a matter of taste, whether you say these are programs and then our syntax is like a synthetic sugar for it, or you say, I mean, your point of view is also completely correct.
It's that for what you prove the rules, right?
Yeah, so for simplicity, I will just think of the program as just doing something on the state and not try to fix a specific language. Yeah, but that's a simplification, and there are different ways to do it. So, for example, we could define the example program. So this is an example program that I will use later. Flip x, which intuitively is supposed to flip the variable x. Which means if my state, if I have a classical state x, y, z, it would just become not x, y, z. So seen classically, this is a very simple program. However, because all the programs actually happen to be linear functions, this thing also fully describes what happens on superposition. So we have x, y, z plus, for example, we have 0, 0, 0 plus 1, 1, 1. Then we just evaluate this flip x on the 0, 0, 0 and on the 1, 1, 1 and leave the coefficients the same. So, but yeah, that's just to give you a vague idea of what quantum programs are and how they fit into this.
Yes. Is it just a random restriction, or is it necessary this to itself? It has to be itself?
Not necessarily. You could have something that like creates a new variable or something. It complicates, when we're talking about Hoare logic, that complicates things, but just like not for, just for kind of reasons of bookkeeping or what the current type is and so on. And if you would try to do something functional programming like, you would probably not even want such a model at all where it stays the same. Yeah. Okay, so now we are ready to ask, what is quantum Hoare logic? So in quantum Hoare logic, we want to follow the same approach that we have a precondition, a program, and a postcondition. We already talked about what are programs. Programs are just, in our abstract view, something that takes a quantum state and gives us a new quantum state. But we need to ask, what are the pre and the post conditions? Yeah. Earlier we had the same question in the classical case, and then we said these are just predicates, which form. It's just anything that, given a memory, says yes or no. But now, well, we could do the same. We could say, given any quantum state. The precondition says, yeah, this one is acceptable, this one is not, and then we could give this whole thing a meaning. But that turns out to be not so nice, because we are in a specific structure, and we have Hilbert spaces. We have these superpositions, and it comes with a certain mathematical structure, and we prefer to kind of be compatible with that structure. So, so one possibility, and the one that I personally am partial to, but there are variants and other things and preconditions that don't even say yes, no, but give you a real number, how much it's satisfied. I don't want to go into that. The simplest case is to say a predicate is a subspace. And then this thing becomes very easy to read. It just becomes for any state psi that is in this subspace precondition, if I run the program on it and get a state psi prime, then it is in this subspace called postcondition. So that's how we read these things. So I give you a little example. Let's say my precondition is, and now I need to write a subspace here. So I want to describe what flip X does. So I can, for example, write a subspace, which is basically like I have here triples of the form, like memory contents of the form 0, y, z. And then I take the mathematical span, which means that I will get just the subspace that contains all linear combinations or all superpositions from things of the form 0, y, z. Yeah? It's not just one cat 0, y, z. It could be like cat 0, 1, 1 plus cat 0, 2, 3 or something, but everywhere 0. So this is like I mathematically just described this. And then I say when I run flip X on it, then I will be in the subspace that consists of the triples 1, y, and z, for possibly different y's and z, but something like that. I mean, it will not be different y's and z, but we are not stating anything about y and z in this case. We're just saying what flip does to x. So I think this is horrible what I did, because I'm giving you like a full mathematical formula to describe the subspaces. It's like, yeah, you won't be able to read anything anymore if I go through any example that is even slightly more complicated. So what we need is, well, first, maybe a nice syntax for special cases. That is easy in this case. We could say we introduce some syntax that if you write x equal cat 0, it means the span of everything that has a 0 here and y and z arbitrary. So this particular example, we can write more compactly by just introducing suitable abbreviations. But we would like to do more than that, because if you think again classically, you may have predicates and then you can use conjunction of predicates, disjunctions, negations, and so on. And you want to freely use them on the things you write in the pre and post condition. And basically what we have here is the von Neumann-Birkhoff quantum logic, which they introduced, of course, not on the context of programs, but it is the structure that we have here. So given subspaces, we can define something similar to a conjunction, namely just the intersection of two subspaces is again a subspace. So if I would say this and something else, then it's just the space of everything that is both in one and the other thing. But conjunction is already more tricky, because I cannot just say something is in the conjunction of the two spaces if it is in one space or the other space, because the resulting thing would not be a space. So it's actually what you use then is the sum of the spaces, or you could also just say the smallest space that contains the union of the spaces, something like this. You have complement, which becomes the orthogonal complement, like all vectors orthogonal to everything in the state. So you can get definitions. These behave somewhat nicely sometimes, but somewhat also not nicely. So it is like in spirit a bit similar to a Boolean algebra. We have conjunction, disjunction, and negation, and nice rules. Here you have conjunction, disjunctions, and a kind of negation, but you don't have all the rules. So some things hold, some things don't hold. And the technical term is a orthomodular complemented lattice, just a side note. So with this kind of language, we can now talk about the program flipx in a nicer way. So for example, here I gave an example that says if x is 0 and y is 1, and we run flip x, then x is 0 and y is 1. If we run flip x again, then x is, oh, there should be a 0 here. How do I start it? So then x is 0 again and y is 1. Yeah, but one needs to be careful, one shouldn't be tempted of seeing this as classical propositions where x and y have specific values. It is that we introduced some abbreviating notation that x equals 0 means a certain subspace of the whole thing, and this intersection here means, this conjunction symbol means the intersection of these two spaces. So what I've written here is not a predicate on a set, it is a subspace of a vector space, which is like predicate on a set would be the same as a subset of a set, and here it's a subspace of a space. But by using convenient notation, it very much looks like familiar things. This is a powerful approach. Why? Well, we can do bottom-up reasoning about the programs. Like I told you earlier with the in the classical case, I broke down this, well, complex maybe saying a bit much, this 3-liner program into reasoning about individual lines. Here we did the same. We reasoned about flip x and flip x, and then we have concluded that two flip x's kind of bring this to this. And using predicates of subspaces means that the rules that we get become rather nice rules, because, like not so complicated, because of the fact that the structure we used is compatible with the with how the programs operate. So is there any clarification question on quantum Hoare? So this was like a little, just giving you an idea what quantum homology is, like not really any deep details. Yeah.
So how would you write the superposition of 0 and 1 representation?
Well, I cannot. I could say something like I could write x equal and then
okay.
This. I mean, it's a little harder to explain how I read this syntactic structure, because I can't just say like I just mean that I write this whole formula in this first part here, so I can't really write it as that thing. But I can give a mathematical interpretation to something like what I wrote here, how I translate this into subspaces. What you could also ask, can I write that x is 0 is anywhere in between 0 and 1? But that's actually trivial, because there's only 0 and 1. But if you would have, for example, not a bit there, but an integer, and I say x is 0 or x is 1, I want to have something like that, then I can write that with the disjunction, but we should be careful. It will not mean that it's definitely cat 0 or definitely cat 1. It would also be allowed to be a superposition. We cannot express that this is one of the two, but not a superposition, not in this logic. The next chapter will actually address this question with a magic trick. Yeah.
It would be nice to have some operator where you get from the superpositions not only for a single variable, but also for complex terms. There's a complex logical term, and then you compose them by change these weights that together have to express what you want.
But this term, are you talking about the term like about weighing predicates or about weighing concrete?
One divided by square root of 2, weight for the complex statement x equals blah and y equals blah, and
like
blah, and compose this one.
Like something like this.
No, predicate, exactly.
Yeah. I'm not sure we can assign a meaning to that, because the thing is, since this thing here is a subspace, it's something that is invariant. It contains all vectors invariant over scaling. So at least a natural view of No, maybe you could give a meaning to it. That's a good, yeah, so in a way, you would want that if you write now the same here, x equal 1, that this is just, in this specific case, would be exactly what I wrote down here.
Would be more natural,
But I think it actually feels more natural to the quantum mechanic person to write this one, but it might be. At least it's
not so logical, it's more physical.
Well, the problem is that I think there's a whole, in this case it's this, but because subspaces are also closed under linear combinations themselves, I'm not sure. I think there's a risk that you will very often get formulas that just are very off from what you intuitively would think they do. One would need to see. I mean, I have not thought about this. It's an interesting idea. I'll have to think about it. We can talk about it later. Off the top of my head, my feeling is I can probably define it. I don't know whether it will behave in any way that is like nice to use.
But since it's an extension, you would still.
Yeah, of course. It will not harm us. But the question is, will it be useful for us? But I don't want to go into now. I'm here afterwards also, so we can.
4 5 minutes, please. I'm afraid you have 4 5 minutes.
Yeah, so I will now rush about the chapter 3 ghosts, because that was in the title. So this is a logic that an extension I invented, and basically it expresses some of the things that were already mentioned. Like, for example, there was the question: can we say x is 0 or x is 1, which we would like to maybe mean that it's really one of those. So it is a classical thing. Can we express it? With subspaces, no, because if it contains cat 0 and cat 1, then it also contains the superpositions and other things, like something is uniformly random, something is not entangled. I'm not going into that because I'm low on time. But the thing is, turns out we cannot do these things with subspaces, as I explained, but there's a trick that we can use so that we stay with subspaces for describing predicates, but we can express these things. So how does that work? It works by introducing something that I call ghost variables. The term ghost variables already exists in programming languages, but it's a somewhat different concept, so it shouldn't be confused. So what I'm doing is I'm introducing some hypothetical quantum variables that are not actually in the program, that I just talked about in my predicates. So let me give you an example how I could do that classically. Like classically, I could write something like my precondition is x equals g squared. And where g is not a variable that is even in the program. By this, I just mean this thing is true for some value of g. And this thing here on the right is true for some value of g, which just boils down to saying if x was a square and I run this operation, then x is a square. So nothing very deep. In particular, I could already write this just by allowing to write existential quantifiers when defining my predicate. So I haven't really gained anything from introducing these existential ghost variables because they are just existential quantifiers. So why did I do that? Because when I do quantum, suddenly they cannot be expressed in a different way. So I could say, let's take my program. In this case, it does something called Hadamard, but ignore what this is. And I write something like x and g together. So the variable in the program and the ghost variable are in some specific state that I have defined here. Basically, it's 0, 0 or 1, 1. And then I run Hadamard, and it's again like this. And now I could interpret this. I'm going to skip about how it's exactly done, as saying I can extend the state to a state that contains a g, so that this holds. So any state that can be extended that this holds, if I run Hadamard, then you get a state that can be extended so that this holds. And now the question is, what would that mean? Well, the thing is, a state that can be extended with like another part of the system so that xg becomes phi plus. This is equivalent to saying, so you can prove that this holds if and only if x is uniformly distributed. So effectively, even though this is still a subspace, but on a bigger space with more variables, I've encoded something I couldn't encode. Yeah, so I can have these existential variables, I can express distributions. It turns out I can also express classicality with it, with some other encodings, and I can encode that something is not entangled with something else, and so on. I will skip this example here and come to my conclusion. So I showed you Hoare logics. They describe what a classical program does, quantum Hoare logic, what a quantum program does, and then I rushed over this concept with ghosts, where just by assuming some extra variable, I can express properties that I couldn't express before. And one interesting thing is that even if I run a classical program, I could express something like the value is uniformly distributed by using quantum predicates, which I can't express with classical predicates. So it's an interesting question that could be useful for analyzing classical protocols. And that concludes my comment. Thank you.